We've just finished up at the keynote this morning where Jennifer showed off her lie detection with the EEG, and that was an awesome keynote, as I was saying earlier. If you could just tell us a bit more about yourself.
Thank
Jennifer.
you. Yeah, so my name is Jennifer Marsman. I've been working for Microsoft for the last 15 years, and my passion is machine learning. I got my degree in artificial intelligence and machine learning 15 years ago, but honestly, that means so little because we've just had such advancements in the field since then. 15 years ago, problems like automatic machine translation and facial detection and speech recognition were all still out there. We're still science fiction, and now they're all essentially solved problems. So it's so exciting to be part of and getting to work in machine learning and having something that I love so much be such an exciting thing in technology right now. That's been really fun. And my role at Microsoft is a lot of coding with customers. So I work with them and help them solve their challenging machine learning problems. And then I also do a lot of public speaking as well.
Okay,
so
awesome.
Yeah.
Great. And Tim, yourself?
And I'm Tim, and I've got a few years on my buddy Jen. So I've been working with Microsoft since 1991. I worked on some server teams in the late 90s, really exciting times in Redmond, Washington. Since then, I founded a number of technology companies. Jen and I share a passion for a few similar things. And frankly, machine learning has changed my life, our life, in the last 2 years. It's just taken such a leap, which allows us to do computer vision at scale and accuracy that was never even dreamed of before. Not just faces. I mean, we could see objects at distance. We're solving some really interesting world problems with this type of technology. So that's my passion these days. I'm a tech guy ultimately, but you'd call me an executive, I guess, these days, because I have gray hair, unlike my friend Jen. My kids are old, her kids are young.
And that keynote, like I said, was really awesome this morning. We're using the EEG for lie detection. There were a few things that really caught my eye there, which were, I guess, being able to reliably predict your husband lying to you, or coming up with lies. I guess one of the questions that I have around that would be, the questions you were asking were very binary, true or false, yes or no.
Mm-hmm.
Have you taken it further to actually try and get him to lie in I guess, in a less binary way?
Yeah, that's a good question. So with my initial work, I really wanted to make it binary just because I wanted to see if it could be done. And I was trying to make it very clear. So the questions that I asked, as I showed in the keynote, were very yes, no, easy to answer questions. What year were you born? Like those types of things that had very clear yes or no answers. There is a concept in machine learning, if you have probabilistic algorithms, of getting back not only a response, but also a confidence level in that response. And so some of what you're asking could be accomplished with that by, like when I did the example where I was asking my manager, certain things, you could see that when I got the results back that there was a confidence level with them. Mm-hmm. So how we think this is a lie and here's how confident we are, and we think this is the truth and here's how confident we are. And so when you are thinking about questions like that where it may be more shades of gray, not a clear yes or no question, those confidence levels could be used as well.
Sure. And I guess with you mentioned about the more greater than 3 classifier.
Yeah.
So. Yeah.
So applications of that. So there are a number of techniques to do machine learning, and a bunch of different algorithms. I'm sure people have heard, Bayesian networks and decision trees and linear regressions and neural nets and some of these terms thrown around. But they're all kind of good at different things and support vector machines. So with a binary classifier, they're actually much easier because essentially, like what an SVM does is essentially, tries to draw a line between kind of the one side and the other side is what it does. So if you think about it, if I had something, like, imagine there's an XY axis right here. I'm sorry, I'm going to try to do math on the fly, but bear with me for 1 second. So if you had an XY thing and two factors that affected your thing. So let's say we're trying to predict disease or something, and the age and the size of a tumor maybe or something like that, or things that you were plotting. And then if you represent all of the little ones that are malignant one way and all the ones that are benign a different way, something like that, and then you drew a line to try to separate them like that, that's kind of essentially what an SVM does, is it finds the line that separates them the best. But then you can do that in essentially, imagine we have 3 features now. So there's 3 different things that go into effect when you're trying to make the prediction. So if you do it that way, then imagine a 3-dimensional space where we're plotting things in 3-dimensional space now. And now it finds the plane that best separates them. And then, SVMs are really great because they can actually scale to lots and lots and lots of features. And it's hard for us as humans to think in 4 dimensions, 5 dimensions, and 64 dimensions, and hundreds of dimensions. But SVMs can actually do that really well. And they draw essentially a hyperplane between these different dimensions to be able to do that effectively. But essentially, you're just kind of like drawing a line or a plane to separate those, okay? And so that makes it very easy when it's classifications. And so when you're dealing with a multi-class classifier like that, where you're trying to distinguish between 3 or more, a very common way to do that is a one versus all approach, where you essentially say, here's all the things that I think are, class A versus everything else. So you kind of almost do yes, no with class A, and then yes, no with class B, and yes, no with class C, and then you can apply all of those together to find the answer. Okay. So just because that makes the math a little easier.
So Liam, you successfully pulled the engineer out of Jen.
Yeah.
I hope you're happy. I think what's most important about Jen's keynote is she picked a use case that a common audience could understand.
Yes.
Lie detection. In a broader view, what's so awesome about what Jen is doing is strictly neural interfaces. The neural interface has the capability to make people who are totally sound of mind yet have lost control of their bodies, multiple sclerosis, cerebral palsy, quadriplegics, there's millions of people around the world. The neural interface has the capability to change their lives and make them wildly productive citizens of the world. And I think that's what's most exciting. The lie detection use case is a great strategy for getting everybody to boldly understand what the heck she's up to. But then you listen to the engineer side of Jen, it's like, right?
Well, I completely agree with Tim. I love it's honestly the situations where we see machine learning helping people and technology in general helping people that are so exciting. Like one of the things I showed in the keynote was the paraplegic example, where there was someone who was paralyzed from the neck down, and then he could use the power of his mind and his facial expressions and such to be able to use EEG to control an automated wheelchair. And so scenarios like that are so cool. There's something else, some other work I've been doing in conjunction with Ranveer Chandra in Microsoft Research and some other folks. So Ranveer is doing this amazing stuff using IoT and machine learning and drones and this really cool cutting edge networking research to try to solve world hunger, essentially. Wow. It's really amazing stuff. So basically what he did was, there's a real problem with hunger. Just the rate of population growth in the world is growing much faster than our rate of food production. And so the problem he was trying to solve is, okay, at some point we're not going to be able to feed everyone. How could we use technology to be able to better produce food? And so one of the ideas behind that is a concept known as precision agriculture. So I wasn't familiar with this beforehand, but it's really cool. So it's the idea that right now we water a field like homogenously, right? You use sprinklers and stuff, or farmers take and just water their fields, everything the same. But fields aren't actually uniform. Like if there's a little dip in the field or something like that, the water will run down, and that area is actually better watered than the area at the top, or the area on the slope that is going to lose that water faster. And so if you apply precision agriculture and only water the parts of the field that actually need to be watered, you can actually save a bunch of water, a bunch of money, and use other techniques to be able to kind of increase your yield as well by using machine learning to predict the most accurate time to plant and things like that. So there's a whole bunch of really amazing research that's being done in that field, and they're using machine learning as well as some IoT, so sensors in the ground to measure like where water is, and that's precision irrigation, but you can also do it with fertilizers and other things as well, to be able to tell where do I need to plant, where do I need to water, where do I need to apply, change the pH level of the soil, like all of that stuff. And it's just really, really amazing work. And so they use the IoT data, but the problem that they had was that the sensors are actually really expensive. It was over like $1,000 per sensor. And I was like, how could that be? Like, Ranveer, explain this to me, because I can show you Adafruit.com. Sensors are actually really cheap. What's the problem here? But it turns out the problem, and then my second thought was, okay, so it's not the sensor, because that's actually pretty cheap. And then the next thing was, okay, is it the power, right? Because in the middle of the farm, if you need to charge these things, how does that work? But they actually use solar panels, and a solar panel is maybe $50 to $100. It's not that expensive per sensor. So, okay, now we have that, the actual sensor, the solar power, like where is all this extra cost coming from for $1,000 per sensor? And it's actually in connectivity, right? It's getting that signal off of the sensor and sending it to the cloud to be able to process it. Because if you think about like trying to use your cell phone in like a farmland area, like in some of the rural areas, there's usually not as good of cell tower coverage. And then wireless is awesome, but it only lasts like, as far as your house, right? It doesn't stretch that far. And so Ranveer, who's a networking expert, had the idea of using this TV white spaces. So essentially, these are unused television stations sending data packets over them, and then you can use that as an internet. And those are actually much lower frequency wave signals, so they stretch much further, right? You know how far a television signal, station broadcasts, and it stretches really far. And so he's actually using that as an internet, where you have to of course work with the local government. You can't just go start sending data packets on over the TV channels. But he's stood up some pilots in Kenya and a number of other places, India as well, researching this technology, and it's so cool to see like what can be done with machine learning and in the precision agriculture field.
Probably in the UHF band, I'm guessing.
Yes.
That's awesome.
Yep.
Yeah. And Tim, earlier you were just talking about the projects that you're working on, collecting a lot of consumer level data and running that through machine learning.
That pales in comparison to what we're just talking about. The Internology company does some really cool software. I mean, most of the world knows us for our work at our broadcast TV software work. CNN and a number of other entities. But yeah, computer vision, as I mentioned, is my passion these days. And
you're not selling that well enough. So Tim's company wrote the software that is used on CNN, like all the presidential elections, like in the US and stuff, when there's like a TV person like on stage, like delivering, they're using his software to do that. Like all the live broadcasts, like the night of the elections was his stuff. So he's not selling that nearly well enough. That's really cool.
I should sell it.
Yeah.
Better. I was watching CNN this morning here in Australia, and sure enough, there's some, English broadcaster from CNN International using that software.
That's so cool.
So 250 million people at a time watch the use of that software. That's something you'd be proud of. It also, since you're an engineer at Microsoft, you'd appreciate that it has an SLA of 100%.
Wow.
On broadcast TV live to 250 million people, you cannot crash. The software has to run 24/7, and it runs on Windows. Yeah, so that's cool stuff. But cancer research, we're rendering molecules in real time so that cancer researchers in the HoloLens.
Yep.
So that cancer researchers can construct proteins that attack the cancers, effectively curing certain types of cancers. The shame about the Internology company is most of the work is NDA. It's protected. I can't talk about it. There's some really cool stuff that goes on in that place, and we do build software for the big software companies like the one Jen works for, and its competitors and other stuff like that. But there are there are projects that I'm particularly proud of, and that would be one of them. The CNN thing, but you know, just as much stuff in biotech and cancer research. It's amazing. Well, Jen and I share this love of AI, and just amazing. Don't you agree that in the last couple of years, man, the curve is just going like this?
Yes.
I mean, imagine a world where in an inexpensive surveillance camera, we can identify a weapon from 1,000 feet away the minute it's brandished. You know, you save one life doing that type of stuff, and it makes it all the hassle worth it. That custom vision, Microsoft Cognitive Services, custom vision is the coolest tech I have seen come out of that place in years. I have a demo here. Shoot, we're being recorded. I already blew it. I have a demo that's the flagship Keynote Demo at Ignite. I'm going to be on stage with Satya Nadella, the CEO of Microsoft Ignite. This demo is so awesome that it brought him to tears. I'm going to do it here in my session later on, and hopefully they don't find out back home. But it has everything to do with object recognition and recognizing disease and disorders in the human body in X-rays and MRIs and ultrasound images. I mean, computer vision and machine learning truly can help save lives. And it's just the last 2 years, so fun. Fun stuff. Now you got me all excited.
Do you guys in the audience have any questions you'd like to ask?
All thousands of you?
I was thinking something along the lines of what your first question was about, not asking the binary yes, no, but around people having to recall information to determine if they're lying or not. And if you looked into that sort of like, 10 years ago, did you do this X or Y?
Sure.
That might skew the
Sorry, just to repeat the question for the cameras. That's going back to what I was asking earlier about the binary classification.
Yeah.
And whether or not you've been able to detect if people can recall memories and experiences, and to determine if that was based on a lie, or is this?
If you looked at someone having to recall something to determine if they were lying or not, like something that happened a week ago, they had to think about it before they could actually answer the question.
Okay.
Rather than having that sort of binary yes, no.
Right. So not in V1. The short answer to that is not in V1. In V1, I just wanted to see, hey, is this even possible? So I was testing with very clear yes, no type questions, and tried to make it very simple. But that is definitely something I've considered for V2. And for V2 also, I wanted to use non-yes or no questions, because it was very, either yes or no, and that's less exciting. Because when you think back to one of my original goals, which was, or one of my original thoughts when I was, beginning this work, it was like, hey, if the truth, when you're telling the truth, that activates the recall centers in your brain, and when you're lying, that activates the creative centers in your brain. The questions that I was asking didn't really do that, if you notice, because really what you're doing is you're thinking about the right answer, and then sometimes you're binary flipping it, right? So you weren't really ever using the creative centers in your brain. So if I ask you a question, instead of saying, were you born in 1978, yes, no, I could ask something like, what year were you born? And then they either have to say the right answer, which could be 1978 or whatever, or they have to make up an answer on the fly. And so that's going to use that creative a little bit more. You know what I'm saying? And so that's one of the ideas for one of the next iterations, is to make sure it's more non-yes or no questions, but questions where they do actually have to think and recall something. So yes, that is something I have planned, but I didn't do it for the first version just because I wasn't sure how harebrained crazy. I mean, it sounds crazy when you say it out loud, like this whole lie detection thing. So I wanted to kind of test it with very clean data first before trying things like that. But it's a very good thought. It's a very good thing, and it is something I'm thinking about doing next.
Yep. And
hi, my name's Adam. So based off, I guess, what Tim and Jennifer, you were both saying about inexpensive equipment. So you're talking about you could go to Adafruit and go to, and get your sensor. I myself look for, I'm a bit of a hobbyist with electronics and sensors, and I see they are pretty cheap. and also with the cameras, they're inexpensive. So would you say the majority of the, I guess, the magic here, or where the strides that we're taking in this field, that's coming from the software point of view?
Can I take this first?
Is it coming from, and like for with your example, Jennifer, the machine learning and the Azure machine learning kit, would you say that that's sort of that closed box system, that's sort of, developed by Microsoft, and maybe the software that you're using, I'm not sure what, but I'm sure it's proprietary. Is that where the sort of the, I guess the magic is coming from, whereas it's stopping someone from, such as myself, maybe at home, if I wanted to, with a, let's say, a Raspberry Pi camera, detect or distinguish the difference between, a dog or a TV, where does it come in? Where's the majority of the work?
Can I take this
Yes,
first?
you can take it first.
Adam has a very perceptive question, and when I say that machine learning has changed my life, it's because a couple years ago we used to do this with 3D cameras, like a Kinect device. Very expensive device, magical device, but had some limitations. Not only its cost, but it can only see 15 or 20 feet. Right? The type of technology I'm talking about now uses commodity cameras. The camera in your iPhone is $4 at quantity. I don't know if you knew that. Or in an Android. It's a $4 camera, right? Software has changed so dramatically because of machine learning that all that stuff we did with the Kinect, we now do in software, solely in software, which makes these solutions really inexpensive. And of course, if you use like the cognitive stack at Microsoft, we're talking fractions of a penny per second. So we're solving problems at scale, performance, and cost now that, God, you would ask me a couple years ago, I would have said, no freaking way. It's people like this who are just paving the way in machine learning. Very exciting stuff. Did you want to augment that?
I did want to augment that, actually. So so machine learning has made some huge strides in just the last 5 to 7 years, where we solved facial detection in an image and things like that. And I think the question was, where is that magic coming from? And there's really a couple things that I think have led to that. One of them is the fact that we have data storage is so much cheaper now. Like, it used to be really expensive to store off all that data, and you brought up the point of IoT as well. And with IoT, when you have all these things, in the Internet of Things, all these things sending, here's my state, here's this data, we just didn't have a way to store all that cheaply, 15 years ago when I graduated, and now we do. We have clouds, Microsoft has, Azure, and there's a lot of other great clouds as well. So we have hardware where we can store a lot, with Moore's Law and such, we can store a lot of data for not a lot of things. The computational power with Moore's Law, we can be able to compute things faster and faster. So with kind of our processing power increasing and then the cost of storage decreasing, that kind of led to this magical moment in time where it's like, hey, we can afford to store a whole lot of data. And now we have this computational power, which is easier to use, which can allow us to draw better insights from all this data. And so that's why it was really kind of a ripe field for machine learning to step back in, because it was actually kind of semi-popular in the 80s too, and then we had what we called the winter of AI, the winter of where it kind of fell out of vogue because things weren't working as well. But now that we have processing power available so easily and data storage is so cheap, it's making it a lot easier to do this. And so a lot of people, I'll go to these companies and I'll see they have all this data that they're collecting and they're not doing anything with it. And it's like, okay, how can we use this data and derive some insights and find patterns and then be able to make predictions and better manage inventory or predict sales numbers or all of these other things. But yes, I think you make a good insight that IoT is kind of tied into that, because with all these sensors, you can use that data and then use it in smart ways. So yeah, I think IoT has helped feed in as well to machine learning.
I love that you brought Dr. Moore's Law into this. You're too young to even know Moore's Law. That's awesome. Did you know that we're on a, speaking of Moore's Law, no one can tell me that that's slowing down. That's essentially, Dr. Moore made this uncanny prediction that is still true today that says you could stuff twice as many transistors on a circuit board every 2 years, right?
I think
what it equates to us is computing power.
I was going to say
And
they reworded it, didn't they, from transistors to power, computing power.
Well, and it spawned a bunch of other laws. Like Tim's law says it's going to be cheaper next year. It's going to be faster and cheaper, right? But we're on a collision course in 2025 that the Intel company's CPU will compute at the same speed as the human brain. That doesn't mean that the machines will be smarter. It just means they'll be able to compute wildly faster, which means machine learning in 2025 is going to solve truly difficult problems. The stuff that we couldn't even think of, world-like problems. That's a world we all want to live in, right? That's a fun world. Yeah.
Yeah.
Did I blow you away with
You
that?
have. You've completely blown me away.
Yeah.
Well, if the machines take over, they're going to forgive all our debt. So there's the good news.
And then we can just sit back and retire on the beach, hey?
Or be slaves to the
or be
machines without debt.
Okay, so.
Yeah, so there's a bunch of other things that have been done in Microsoft around using machine learning for predictions as well. There was one really cool study. This is somewhat related to the world hunger thing again, but we did one prediction where we were trying to figure out when is the best time to plant peanuts. It was actually some farmers, and they were planting peanut. They planted peanuts at the same time every year, and so the researchers in that area said, okay, let's build a model and see if we can better predict based on all this data we have of when the optimal time to plant peanuts is. And they actually took that data, made the predictions, and then made it available to all the farmers. So they had provided like, we'll send you a text message, all these farmers, when it is the proper time to plant. And the traditional time for planting came and went, and 700 people had signed up to be able to do this and say, okay, we want the text message to know the best time to plant. And the time of the traditional planting came and went, and some people got nervous and was like, we haven't gotten the text message yet, let's just go ahead and plant because we don't want to miss it, right? And so 300 out of the 700 actually just went ahead and planted at the traditional time. And then the text message actually came about 2 weeks later or something. It was like, okay, this is going to be the best time to plant based on our models. And so the remaining 400 people planted their crops then. And it turned out that it was awesome that a bunch of people just went ahead and planted because that gave us a control group, right? So now we had a control group as well as a variable group. And so they found that the people that had planted when the algorithm said had a 30% higher peanut yield than the people who planted at the traditional time. So it was really cool that we were able to have that data and be able to gather it and such to do that. But it's stories like that that just get me so excited, and the work like Tim is doing in cancer detection and things like that are just really, really amazing.
Wow.
So yeah.
Well, the future just holds so much for us, doesn't it?
It does. It does indeed. Did you have another question?
Yes, I did. Sorry.
I'm just going to ask it. So basically, so a lot of your work is obviously based around the software aspect of things, but with relating to the speed at which things happen, and I guess that aspect of computing power. Are either of yourselves involved in things such as like FPGA work and design to, I guess, combat that current maybe limitation that we have with traditional CPUs? So for myself, there's a lot of, like, coming out of uni recently, there's a lot of like thesis projects around, machine learning using, FPGAs and specialized hardware to, like, for the purpose of speed. Are either yourselves involved with that, or maybe can elaborate further on that?
Well, yeah, Adam is a smart young man. Are you and your brother employed? Because we need to talk. Wow. So yeah, I mean, we have all this. And I'd love you to weigh in on this. We've got this balance between all this awesome power in the cloud right? But we have these internet dependencies to the cloud. And without an internet connection, there ain't no cloud, right? So I constantly, this morning I was on a conference call, to get all this power pushed to what we call the edge, like to have it run on the device in the hardware. Well, I'm a Windows guy, right? That's, I was working on Windows in 1991. That's a tough concept for me. Certainly in computer vision, we have to do a lot on the client side before we get a face and throw it up to the API, right? But to do that on the edge is a totally different world. And we've got some progress in embedded versions of Windows, thank God, that are really going to help. But that is a dilemma that we're going to have to overcome. We have a dependency on the cloud now, and what's the hybrid Azure Stack, the hybrid OS.
Yep.
There's some, and the other competitors are doing it too. There's help coming, but it's a very real problem that you bring up, because you want that power on the edge, and you don't want to have to round trip, like the demo I'm doing. I'm going to round trip to a cloud provider on the West Coast, right? I really was lazy. I should have switched it out to the Azure cloud thing out here, but I didn't. So there's some latency. Interesting problem.
Yeah, it really is. So in answer to your question, I'm not directly involved with any of the FPGA work at Microsoft, but there is a lot of work being done. So we have solutions right now where you can run kind of machine learning in our cloud. You can also run on GPUs, and then there's FPGA work being done. I mean, we have quantum machine. There's quantum computing. We have a whole quantum computing team that's thinking even next generation after that. So there's some really, really amazing stuff being done, in Azure, all up on computational power. And then I would echo what Tim just said about computation on the edge, because if you look at kind of what all of the major providers have announced in the last year or so, Microsoft has made announcements about like the IoT edge and such. Google at Google I/O, they were talking about TensorFlow Lite that can run there, and Apple and Facebook and like everybody is talking about this right now, being able to run on device. And when you think about it, it's true. When you think about a scenario, so I'm from the Detroit, Michigan area, which is where in the US we make a lot of cars. And so the connected car scenario is a great example of that, right? You don't ever want a car to be making a call to the cloud or have any network dependency and then getting a response back, because the internet could go out and then that car's going blind. Like that's just, it's not going to happen ever. So you need to have all of those models actually on device in the car to be able to do that. So does that mean the cloud is irrelevant? No. So in machine learning, there's really two parts of the process, right? There's training a model, and then there's actually when you use the model and call it and use the predictions that it makes. And so when you think about the scale of data you need in order to do a fully autonomous vehicle, you need cloud scale support, right? You need to have, if there's just terabytes of data coming from each car, because there's so many different sensors on each car. So if you have, and then scale that to, all these cars we have in the world, you need a cloud to be able to do something like that. So there's kind of the training phase where there's different cars and they're all sending their data up to the cloud, and then we can do processing in the cloud. We can then make decisions and build models and have all that work where we train a model and build the models there and test the models and see how well they perform. And then we can actually take those models and we want to push them to the edge, and then when they're called at runtime, when you're actually driving the car, you would want to be using it there in the vehicle. And so when you think about that, you can see how there's nice examples of how the cloud and on device can work together beautifully in those types of scenarios. So I'm driving along and I don't have my network dependency and stuff, but I did use the power of the cloud to train it. So. Okay,
so I think we're running out of time here now, so we'll wrap it up there, and I'll say thank you, Jennifer. Thank you, Tim, for taking your time to join us here today. And I hope you guys enjoy the rest of NDC.
Great.
Absolutely. Thanks, Liam.
Thank you, Liam.
Thank you.